Very warm welcome, everyone, this morning. Hope you had a good party last night. Looked like it, at least, from looking around. So I'm going to talk a little bit about TCP optimization today. It's a technology that is gaining significant interest over the last couple of months, and I'll talk a little bit about why that is, and I'll show you some test results, how it works, and what it can do to your network. But before going into the presentation, I'd like to show you a very short video. I've been personally doing some testing with service providers around the Europe, Middle East, Africa region. This is a test that we did with one particular service provider who was doing testing on TCP optimization. So what they want to do is their goal is to be the best network in their country and to remain the best. And in order to do that, they sort of measure every half year how is their performance compared with their competitors in their country. And they saw that the gap was narrowing a little bit, so they were wondering if there's any technologies out there that can help them get better performance. So this is a test where we showed on a 4G network, LTE, in relatively bad coverage area, what the results could be from TCP optimization. So on the left-hand side, you see these two same mobile devices, Samsung devices, connected to the same network, same eNode B, same radio network, everything the same. The only difference is the right one is connected through a TCP optimization, to a TCP optimizer from F5 networks, whereas the left mobile device is just going straight to the mobile network, just like their network runs today. So as you can see, we were able to increase the bandwidth from roughly 10 megabit per second to 14 megabits per second, just by playing at the level of the TCP stack. So this test really proved that there is some significant gains to be had out of this technology. So I'll talk a little bit about market trends, what's happening in the industry, and why all of a sudden people are so focused on this technology. There's a couple of parameters in your environment that make that happen. And then I'll talk a little bit about the technology, how it works, how it's deployed, and show a bit more test results of what we've seen in live networks. Changing environment. So these are the two main drivers that force people to look into different optimization technologies than what they were looking into before. If you look at mobile operators, they've been deploying video optimization technology, web optimization technology. They've been deploying transparent caching, all these techniques. If we look at what's happening with SSL these days, the feedback I get from several operators in Western Europe is that roughly 50% of their total traffic is SSL, running on port 443, which means that 50% of the traffic you can't look into the content anymore, so forget video optimization, forget web optimization, forget transparent caching. None of that really works unless you're going to break open the SSL communication, which is obviously from a legal perspective a very tricky thing to do. This is fueled by the Snowden revelations, right? People very concerned about privacy, so more and more websites turning on SSL. But also SPDY is an important contributor to this. SPDY, which is the new protocol introduced by Google, and now being adopted by Facebook, by Twitter, by some of the very large players in the internet. And SPDY runs on top of SSL as well. A little bit outside of the context of this presentation, but also on the video optimization space, we see a significant rise in adaptive bitrate streaming, which actually now allows the client to regulate the bandwidth by itself by monitoring the bandwidth that's available. So traditional transrating and transcoding are no longer necessary because the client can pick the bitrate which he feels from a bandwidth perspective is the appropriate one to use. So just for a very quick, because I know some people know SPDY quite well, others, for some of you, it may be new. But if you go to Google or you go to Facebook or you go to Twitter, you see HTTPS in your web browser. Actually, this is not just HTTP over SSL, this is SPDY, which is a new protocol developed by Google and which solves some of the inefficiencies of traditional HTTP 1.0 and 1.1. So HTTP is a very old protocol, and because of a mobile network having a relatively large latency compared to fixed networks, HTTP is quite inefficient. Browsers try to get around that by opening multiple TCP connections in parallel so that you can have multiple HTTP requests running in parallel as well. But SPDY solves a lot of that problem in the protocol itself. So with SPDY, you can actually start multiplexing multiple HTTP request responses over a single TCP connection. And test results have shown that SPDY is way more efficient over a mobile network than traditional HTTP. And I'll show you in some test results later on how that pans out. SPDY also serves as the basis of the new HTTP 2.0 specification, and there's a big debate in the industry now, content providers versus service providers, because the content providers want everything to be SSL. Service providers, like many of you here in the room, obviously don't want that because you lose any type of control over the traffic. So there's big debates now around introducing trusted SPDY proxies and all that, but that's more of a topic for a separate discussion. So with all this SSL, what's the impact on the traditional optimization technologies? Well, the value of the traditional transrating, transcoding gets diminished, because if it's encrypted, there isn't all that much you can do anymore. Caching, again, reduced benefits. So this is why people are now looking at TCP optimization, because TCP optimization works at the level of TCP. So it sits one layer below all the SSL stuff. So all the SSL, all the SPDY can still be TCP optimized, just as the traditional port 80 traffic, just as any TCP traffic. And looking at statistics from service providers, we see that between 90 and 95% of all your traffic is TCP. So this means that this technology is capable of optimizing 90 to 95% of your total traffic, regardless of whether it's encrypted or not. Doesn't matter. Very quick, TCP is a fairly complex protocol, and you can find a lot of research papers on the internet if you start doing searches on like TCP congestion control algorithms, etc. It's a fairly complicated protocol, but just for the sake of this short discussion here, there's three things you should keep in mind. First of all, TCP is a connection-oriented protocol, right? Before you start exchanging any data, there's a three-way handshake, the SYN, SYNAC, etc. So that takes place. So before you start exchanging any communication, you set up that TCP connection. So you have state in both the endpoints. The second important property is reliability. So TCP provides reliability in the sense that the sender always knows when the receiver has received the traffic that the sender has sent to it. And this is done by an explicit acknowledgement scheme, right? So the receiver acknowledges data received from the sender so that the sender knows, okay, I can move on and send the next data, or I may have to retransmit data if some data got lost. The third important property, and this is essentially where a lot of the TCP optimization techniques start playing a role, is the flow control and the congestion control algorithms. So by means of a sliding window, the sender is going to send data to the receiver and is going to try and ramp up the speed of doing that until the point where packets get dropped. Then, of course, by means of the acknowledgement scheme, you will figure out that packets are dropped, and then you start slowing down your sending rate again. So you get this traditional sawtooth effect, which is happening in TCP. And here a lot of research has been put into by universities, etc., figuring out what is the best congestion control algorithm for any particular access technology. So this is where TCP optimization is going to play a very big role. This actually comes out of a research paper which sort of compares different congestion control protocols. If you look at Reno, which is, for those of you who have a bit of understanding of TCP, this is the most basic form of TCP congestion control. So the sender is ramping up the rate until he detects packet loss. Then you reduce your congestion window in half, and then you start again. So you get that traditional sawtooth effect. I'm sure many of you have done tests in your labs trying to figure out, you do an FTP session through a traditional rate limiter. You'll see that the rate of your FTP session is typically around half of what your rate limiter provides. That is why. So this is why that happens. So Reno is a pure loss-based algorithm. Loss-based meaning you lose a packet, and then you reduce your congestion window, so you slow down your sending rate, and then you go up again until you lose another packet. Those were the first protocols which were used in the industry. Later on, new protocols were introduced which take into account delay, which take into account trying to estimate the bandwidth. And then the newer ones are what we call the hybrid loss delay algorithms. So what these algorithms do is they still use packet loss as an indication of I need to slow down, but they also measure the delay which they measure on the TCP connection, and the delay is going to determine how fast I need to go down or how fast I need to ramp up. And what we've seen in test results is that these are the best protocols to use in mobile networks. Why? Because mobile networks, they tend to introduce a lot of latency. And if you introduce a lot of latency, it typically means that you're increasing the buffers in your radio network, which usually isn't a very good thing to do. So when these algorithms detect that the latency goes up, they tend to be a little bit less aggressive in ramping up to allow the buffers to sort of flush out. So if you do tests and you start comparing all these congestion control algorithms, you will typically see that with the Illinois and Woodside algorithms, you get the best results on mobile networks. So what's the impact of latency? This is a not so well understood problem. If we do TCP optimization testing, we typically try to optimize two different things. One is optimize bandwidth, like you saw in the demo in the beginning, the speed test, right? Get as fast as possible, high bandwidth as possible. The second thing is web page load time. How fast can I load a page? If I go to Facebook, how fast do all these objects come to my screen and get rendered? And that's a very different thing. Bandwidth is not an impacting factor for web page load time. Or let's say it's not the most impacting factor. You can see in this graph here that as soon as you reach 5 megabits per second, going up to 10 megabits and even 100 megabits per second is not going to have a massive impact in your page load time, which is shown here in milliseconds. So as soon as you reach the 5 meg border, increasing the bandwidth is not going to make your Facebook go faster. It just doesn't work like that. And that's again because of the latency that you experience in mobile networks. You see, if the round trip time goes down, that's where web page load time matters. So one aspect of TCP optimization is also trying to make sure that the buffers in your radio network don't get too much stress from the network. So we try to make sure that we keep the buffer utilization in the radio network as low as possible. And only then you can tune for both speed and page load times. Because we can easily tune the network for getting the best speed test results, and completely destroying web page experiences by means of this. So that's the impact of latency. Impact of packet loss, obviously that's well known. Packet loss, that is the primary thing used by TCP protocol to determine now I need to go down. TCP was designed in such a way that packet loss should be interpreted as a signal for congestion. So when you have packet loss, TCP thinks, there's congestion, there's too much traffic in the network, I need to slow down. Now radio networks tend to lose packets just by means of radio, right? Of course, there's some retransmission techniques at the radio layer, but still, it's not uncommon to have 0.1% or even 0.5% packet loss. And if you lose those packets, it is not necessarily a sign of congestion. It's just a random packet loss by means of radio. So also here, TCP optimization can take these things into account and behave a little differently for a mobile architecture than you would for a fixed architecture. Because as you see, packet loss will always force your sender to go down. Whereas in this case, there may not even be congestion, so there isn't any reason to go down. So by means of some smart techniques, you can try to figure out, is it really congestion or is it random packet loss? Here is another interesting phenomenon. TCP has this slow start mechanism where you slowly ramp up your sending rate. If you use standard TCP technique, which starts with what is called one segment size and then you slowly go up, it requires 3 round trips to get 16 kilobytes of data back to the client. Now, an average HTTP response in the internet is roughly 16K. So that means that for an average HTTP response, you have 3 round trips. Again, if you have a mobile network and you have latency of 200, 300 milliseconds, 300 milliseconds times 3 is 1 second, right? So it's at least 1 second before a portion of your web page starts to load. So one of the techniques here is that you can set in a TCP optimizer is to make sure that you start with a higher initial congestion window, so that on the internet side we can quickly get these 3 round trips because latency is very low. And then on the mobile side, we send all that data in one chunk. So you don't need 3 round trips there. So all these techniques help you improve the web browsing experience. So it's all about high effective throughput, bandwidth, web page load times, try to get them as low as possible, and then flow fairness, right? If you have multiple users sharing the same bandwidth, you should try to make sure that the bandwidth is evenly distributed between all the users we have. So how does it work technically? Where does it sit in the network? Well, essentially you sit in between the mobile network and the internet, right? So typically we would be deployed right behind the P gateway, GGSN. You act like a transparent proxy, so you essentially do proxy the TCP connections, but obviously you don't change any IP addresses, right? So from the client still thinks he's talking to the server thinks he's talking to the client, but in reality there is a proxy in between which proxies all the data in between them. So you have a different TCP negotiation on the left-hand side versus the TCP negotiation on the right-hand side. And that really allows us to fine-tune whatever congestion control we use here, whatever initial congestion windows we use, whatever loss filters we use on the radio side versus what we do on the internet side. So essentially we fine-tune everything for the characteristics of this network, which in this scenario is a mobile network. And this is a wide area network with typically high bandwidth, very low latency. That requires very different tuning. If you don't do the thing in the middle, these things really start doing standard TCP, which is probably good for getting you up to here, but it's not good for getting you over that radio network. So the specifics of the radio network, so the BDP differences, yeah, as I said, I don't have much time to explain all the concepts of TCP, but BDP is the bandwidth delay product. So every time you do some TCP tuning, that's a very important parameter. It's the bandwidth times the round trip time. It's sort of a characterization of how much data you can send into the pipe unacknowledged by the receiver. If you make it too slow, you're not making full use of the bandwidth, so you're leaving some bandwidth unutilized. If you set it too high, then you're going to overshoot the capacity of the network, and then you're going to get packet drops. So ideally, you should try to fine-tune that to the very characteristics of your mobile network. The random packet loss, obviously that can be managed by intelligent congestion control techniques, so that you don't immediately reduce your congestion window in half when you see one random packet being dropped. Buffer bloat issues, so if you're ever interested in buffer bloat, do a search on the internet, you'll find loads of research papers on this. Buffer bloat is that phenomenon where a TCP sender sends to the client. He tries to go up, as long as he doesn't see packet loss, he tries to go up. But the result at some point is that the buffers in the radio network will start to fill up because you cannot deliver it to the client, the bandwidth is not high enough, but you start filling up the buffers. TCP doesn't see that, right? TCP only sees something when a packet is lost. So you're filling up the buffers, and in a 3G network, you can fill up buffers with 2 seconds of data, which, remember the web page load time graph? That completely kills any web browsing experience. So buffer bloat is something you need to keep under control as well. And then, of course, you have mobility and handovers, which give little glitches. Again, these glitches can be managed more effectively with intelligent congestion control algorithms rather than the standard algorithms which are in standard Unix servers. In terms of how this is deployed, this was a very traditional setup of deploying optimization. So people were deploying video optimization, and typically these platforms support TCP optimization as well. So I would say TCP optimization, video optimization is probably the same platform. But the way it's typically deployed is you have a router or a switch here which just forwards port 80 traffic, because port 80 is what video optimizers can optimize. That means that SSL is not going through this. SSL goes straight through. 50% of your traffic today, as I said, is not optimized at all in this architecture. So this is the new way of deploying this. So you put a TCP optimizer in line, which deals with all your TCP traffic, 95%. And then you can still do some intelligent steering using the proxy. You can do intelligent steering to whatever video optimizers you have. And that's a question we very often get these days. Like, I have video optimization there. I still want to continue using it, but my use case may vary a bit. I may want to bypass it for LTE traffic, as an example. I may only want to enable it for certain users under control of a PCRF. So there's lots of use cases that are being discussed now, looking at new ways of how to use video optimization. To finish, a few test results. So these were throughput and web page load times, right? So the dark blue bar is a HTTP large download. Think of a speed test, right? Download one large object over a single TCP connection. The other bar is the web page load time test. This is like lots of small objects being requested which simulate a web page. So here you can see that both on 3G as well as 4G, there is some significant gains to be achieved. I'm not sure if it's very well readable, but this is 20%, 28%. Here you see 38, 33%, depending on whether you have good coverage or bad coverage. In 3G, the difference is even more outspoken. On 3G, if you have poor connection, the result is massive. It's really a big difference. But you can see also here that even in good coverage, TCP optimization gives you a lot of value, but as soon as you go to poor coverage, the results are really ramping up very steeply. The customer I was doing tests with, they were investigating SPDY, and as I said before, SPDY solves a lot of the inefficiencies of traditional HTTP. So their question was like, why do we need to invest in TCP optimization if SPDY already solves the problem to a large degree? So we did a test by showing that you can load a SPDY web page in a non-SPDY fashion. This is by turning off SPDY in your browser, actually, because if your browser doesn't stock SPDY, the web server does normal HTTP. So then you turn on SPDY in the web browser, and they saw an 11% improvement. So web page load time was improved by 11%, or reduced with 11%. Now we turn on TCP optimization on top of it. So then you see that on a non-SPDY case with TCP optimization, we get a 23% improvement. But also for the SPDY case, we roughly get, this is 11%, this is 31%. That's an additional 20% on top. So the message was, with TCP optimization adds additional benefit to what you get with SPDY. So these benefits do add up and provide a lot of value. Last slide. This is the buffer bloat problem. So we had one test with a customer, and it was a speed test. And we say non-optimized 11 megabits per second, optimized 11 megabits per second. Customer said, like, your technology doesn't work. No benefit. We started digging into this. Obviously, it was not completely tuned at that point in time, but what we saw was this, right? So this non-optimized case, this TCP stack goes higher and higher and higher. It fills the RNC buffers with 1.52 seconds of data. Whereas in the optimized case, we kept the latency around 200 milliseconds. So the response from us was, yes, your throughput may be the same, but if you would add a web browsing session on top of it, you wouldn't get much, because with 2 seconds of latency, your browser probably is going to time out and all that. You get nothing through, whereas here we still have the normal 200 milliseconds in latency that we get. So yeah, summarized, it works for 90 to 95% of your traffic. It's really beneficial for your network. We see lots of interest now with all the SSL going on everywhere. And also it's an opportunity to look into redeploying what you already have. If you already have video optimization, this is now also an opportunity to look into different ways of doing things, because the market forces you to do different things. And with that, I would like to thank you very much.
Are there any questions?
Hey Bart.
Hey Jeff.
So with the radio evolving to LT, TD-LT, to high-speed networks, and SPDY doing in-band optimization, don't you see results of optimization disappearing or becoming non-tangible?
Well, I think the last test showed that, right? And that was a valid concern of the customer as well. Because they were saying, yeah, SPDY gives me a certain amount of benefit. Does it really help to add an additional layer of TCP optimization? And I think the results prove that. We provide an additional 20% on top of that. The other test we did, but I didn't show it here in the document, is that we also did a test with Google Docs. So if you do put a document on Google Docs and you download it, it's going to be a speedy download. And again, that's a long-lived connection with a lot of data. Whether that's speedy or not doesn't really help, because there's no transactions. Whether you do that over speedy or just over plain HTTP makes no difference. So again, there we will see the same benefits. So yes, the benefits add up actually, which is a good thing.
Anyone else?
Hi, I've got a question. This machine that is doing this TCP proxy you mentioned, what is it based on? Is it just an x86 and you're using some Linux TCP where you put your congestion control algorithms? Or is it some kind of dedicated hardware and the software?
Well, it's one of the many things we do in F5 on our Big IP platform. So we have Big IP. We come from the load balancing space, right? Providing application delivery controllers. We evolved the product to fit into many different spaces, and TCP optimization is something we've been doing for many years. It's just now the last 9 months that there is an increasing amount of interest in the technology. But it's based on our dedicated platforms. We have virtual editions as well, so you can run it on x86 hardware if you run a virtual edition on a VMware ESX or a KVM hypervisor. So that is possible as well.
I have one question. You show that TCP optimization is done by the operator side, right? Is there anything we can do on the server side? If we can, for example, differentiate mobile users?
The question is a little... I get that question quite a lot, whether you can do something on the server side. There's a couple of complications that may come into the picture. First of all, if you're hosting a web server, you can get people from the fixed network, you can get people from the mobile network, from Wi-Fi network. So first of all, you have to figure out whether they come from mobile, because that's where you will get most of the benefits. Then second, which is probably even more important, is that you don't know if there is already a proxy doing something like this operated by the mobile network operator. If there isn't such a device, then yes, you can provide that benefit and you will see an increase in performance. If the service provider already has a device like that, then essentially what you would be doing is you would be optimizing the path between your server and that optimizer, whereas the optimizer will continue to do his work on the radio side. And that portion you can't really optimize because it's high speed, low latency. So there's many factors that impact that.
Okay, then I'd like to thank you very much for your speech.
Thank you very much.